Okay, so now you have these formulas. Are you familiar with them? Have you been looking at them? Yeah, no, maybe?
I've been looking at them, but I'm having trouble remembering.
I'm having trouble remembering them.
Okay, so that's fine. That's okay. I'll accept it for right now. So what we're going to do, we're going to talk a little bit about some of the formulas and ways to remember them and things like that, right? And so you want to make sure that you learn them, right? You will have a polyatomic ion sheet that will be available for your exam, but it will only take you so far. Mainly it's there for, it's like a crutch, you know? So, and I will often refer to other components that aren't on the polyatomic ion sheet, and you should be expected to know what they are based upon your crutch. Do you understand what I'm saying? So, and I'll kind of talk about that here in a second. But we're going to talk about some of the basic ones, and I want you to kind of think about them and see this process and how this actually works pretty well. Okay, so these are some of the polyatomic ions, right? You should be learning them, right? Because you're going to see them over and over again. And often during the test, you won't have time to sit there, okay, let me go look to see if I have it on my polyatomic ion sheet. You should be able to have a pretty good idea of what they are. So I'm going to go through some of the general rules, and then we're going to play, like, do a little bit of a game, see how well you guys retain these things. Okay? Okay, so these are some of the common polyatomic ion tables, right? And all of these here, these are called oxyanions. The reason why they're called oxyanions, let's see, come on. Oops, got carried away. What do you think that oxy stands for?
Oxygen.
Okay, yeah, so oxygen is going to stand for oxygen. Oxy is going to stand for oxygen. And what is an anion?
A negative polyatomic ion?
It is a negative polyatomic ion. Okay, so there are a couple of ways. Oh, go ahead. Did you want to add something? Okay, so I'm going to give you, we'll go back to that list. So an oxyanion, so it has to have oxygen and it has to have a negative charge associated with it. Pretty simple, right? Not too hard to remember. Oxygen and a negative charge. Okay, so let's go back to the slide prior. So in this case, right, all of these guys are oxyanions. Okay, now if you take a look at these oxyanions, so we have, in this case, dihydrogen, 2 hydrogen. Okay, 2 hydrogen, phos, that means phosphorus, and 8. And that 8 refers to the common number of oxygens for that particular ion. And it's going to vary between different ones. So phosphate, let's see. So this dihydrogen is going to add a plus for each one. Each hydrogen has a +1 charge associated with it. So phosphate.
So -3, right?
Yep, so overall, phosphate is going to have a -3 charge. Phosphate alone, that one is going to just be PO4 3-. Okay? Okay, so now if I lose a single oxygen, one oxygen down, I call this now phosphite. Oops. So chemical formula for that would be Losing 1 oxygen, 3. And it's still going to be 3 negative. If I lose another oxygen, it's called hypo. What does hypo mean? Not hyper, hypo.
Low.
Low. Hypophosphite. Not shite. So what do you think the chemical formula for that's going to be?
PO2 negative 3. Or 3 negative.
Oops. Got carried away. And there's one more I want to go over. Well, per for hyper phosphate. Okay, so what do you think that one has?
PO5. 3 negative.
So now you noticed in all of these cases, did we change the charge on the ion?
No.
What is changing?
The amount of oxygen.
The amount of
Atoms.
oxygen. Okay. Now this is true primarily for most oxyan ions. There's one exception, and that's going to be manganate. Okay. And I'll talk about that one later. In the case of permanganate is specifically the one I'm making reference. Okay, so manganate itself, I'll talk about it right now. Okay, so manganate, you would assume since this is permanganate, then you would assume that the next manganate would be MnO3, right? Would that make sense if we obeyed the rule that we have up above?
Yes.
Yes.
But manganate is an exception. So I would write down in big, black, bold letters on my notes, exception. Manganate is actually MnO4 2 negative. Okay, and again, big, back, bold letters, exception.
Why is that, Dr. Henry?
You know, to be honest, I don't know. I think it's just, it was one of those things that were done before they established the rules. And so they just kind of kept it.
Okay.
So you'll see a couple of those things that happen along the way. You know, there were rules, things that were done before the rules were really established. And so they kind of keep them along those same lines.
Okay.
Okay. So this is the exception. Okay. You guys got that?
Yep.
Okay. So now you kind of see how this works. I'm going to put up an oxyan ion, and then I want you guys to go through it and name it and go through the same steps of knocking it down and give me the name and the chemical formula for it. I'll give you the starting point, and you guys can see if you can figure out the rest. Can I erase this part here to give myself room?
Yep.
Okay. So let's start off with, I'm going to clear everything. So let's start off with sulfate. Okay, so chemical formula for sulfate is SO4, 2 minus. Okay, so what would be the one that has an additional oxygen added on it? And how would I write that chemical structure? What would that guy be called?
Persulfate.
Okay. And its chemical formula?
SO5 -2.
Okay, so what about the one that has one less oxygen?
Would it be SO3 -2?
Okay, what would it be called?
Hyposulfate?
No, not hypo.
Sulfite.
It would be called sulfite.
Oh,
Okay. And what about one that's one less oxygen?
Hyposulfite.
Okay. That one's hyposulfite. And remember, it's ite instead of 8.
okay.
So SO2, 2 minus. Piece of cake?
Mm-hmm.
Yes.
Kinda.
Okay, so I'm going to give you one more and we'll see how well you guys do on it. So let's do nitrate. So nitrate starts off as NO3 minus. Okay. So the one that would be one oxygen more is going to be called
Pernitrate.
chemical formula.
NO4 negative.
Okay. Now I know that there's more than one person in this class, and you want to make sure that you're participating, because if you're not, what's going to happen?
Not a good score. I don't know why every time I think, I don't know why every time that there's an oxygen, I think it's hypo.
Nope. So remember, hypo just means less, right? So you want to sit there, it just means one less oxygen, right? So, and it's only gonna go with ite. So it has to be one less than the ite.
Okay.
Okay, so what would be the one that is one oxygen less than nitrate?
Nitrite.
Nitrite?
Yeah.
Okay. Okay, and that chemical formula is
NO2 negative.
and the one that's one less than nitrite.
Hyposulfite.
Hyposulfite?
Mm-hmm.
You mean hyponitrite?
Yeah.
Yeah.
I use that for reference.
And so that's going to be no,
Negative.
no negative. Okay.
Dr. Henry, I get confused when there's an extra thing at the front. Can we do one of those?
Yes. So like you're saying, if
Like
I
the
have,
top one is the dihydrogen. That one's easy because it's just hydrogen, but when it's something else with like a different number, I get confused.
we're working up to that. We're not going to get there yet. We're working up to that because that's where we're going to start talking about our ionic bonds.
Okay.
Right. So don't worry, we'll get there. I promise. Promise. Okay, so you guys see how it works, right? So what if I had something like chromate? So one more than chromate would be called
Perchromate, dichromate.
perchromate. Per-dichromate, sorry. Per-dichromate. And then what would be the chemical formula?
CR3.
Be just 6 oxygen atoms, right?
Okay. Is it 6 oxygen atoms? Per?
Oh, 8.
So it'll be Cr2 O8 2 minus. Okay, so one less than dichromate would be called
Dichromate.
okay, and then what is that going to look like?
CR2O7 negative.
Cr2. Is it O7? Because isn't chromate, dichromate,
Oh.
O7?
Oh, 6.
O6.
O6.
Yeah, I kind of threw you off because I didn't put that one in between the two. So we know that this guy falls in the middle. Come on, got to keep you on your toes, right?
Yeah.
And the one with one less oxygen than the chromite,
Hypodichromate.
hypo. Okay, simple, right?
Yeah.
These are
Yeah.
like gimme points, right?
Good morning, floor. How are you?
Okay. So we're good so far? Simple?
Yeah.
Yeah.
Yes.
For
Okay.
the per dichromate, is that a -1?
It is a -2.
Okay,
My handwriting just sucks.
gotcha.
Okay, let's go on. So we've talked about nitrite, we've talked about sulfate, and we talked about phosphate. Now, the rule is that pretty much if they're in the same group, they're going to kind of behave the same way. Now, we know that phosphorus and nitrogen are in the same group. They're right underneath each other. So let's look at the periodic table, maybe. Come on. Some days my computer just does not want to behave. Can you see my P table?
Yep.
Okay. So look where nitrogen is located at. I'm going to clear the screen. Okay. Nitrogen and phosphorus are both in the same group. However, Nitrogen has a -1 charge, and phosphorus has a minus what charge? Or phosphate. Nitrate had a minus what charge? NO3, you guys remember?
NO3 negative.
It's NO3 negative. And then phosphate had a what charge? And how many oxygens?
PO4 3 negative.
Okay, so they're different. Even though that they're in the same group, they are a little different from each other. And that's the one thing that I do want to point out to you, that these two guys are going to be different. However, if we have anything after phosphate, is going to behave like phosphate. So if I have SO4, what is going to be the charge on that SO4? I mean ASO4. What would be the charge if you expect them to behave like?
3 negative.
Okay, so arsenate, which this guy's called, is going to behave like our phosphate. What about antimony, SP04? What's going to be the charge on that guy?
-3 negative.
And we'd call it antimonate. Okay, you guys get that?
It just bases off of how many electrons it needs to get to the noble gases, right?
Yeah, in this case, except for nitrogen. Nitrogen is the exception,
Okay.
right? And it has to do with where it's located at. Okay, so for like, let's say, we know that sulfate, here you go, erase this. Sulfate, what is the chemical formula for sulfate?
SO4 2 negative.
SO4 2 negative. So what would I expect the chemical formula to be for selenate? Named after Selena. So Selena should answer this. Is Selena here? Oh, Selena isn't here. Never mind. Making fun of her. She's not even here.
For selenium?
Yes?
If it would-
Selenate.
Oh, okay. It would be SeO4 2 negative.
Okay. And what about tellurium?
3O4 2 negative.
Yeah.
Or tellurate? Okay, so you guys get that?
Yes.
Okay. Okay, so you guys should be feeling comfortable with the 8-ite, hypo-ite, and per-ate. Feeling good about it? Yeah? No? Maybe?
Mm-hmm.
Yeah.
Okay, so let me clear. Okay, so we've talked about the naming. You're feeling good about it. It's not a problem. Okay, so let's talk about the type of bonds that are going to be formed. So those are ions, right? So they're polyatomic ions. So we know that we have two types of bonds, right? We have a case where we have an ionic bond. An ionic bond is where you're one guy is going to be giving, the other guy is going to be taking, but there's an exchange of electrons, okay? And we have what we call a covalent bond. A covalent bond is sharing of electrons, okay? So, and you got to think about it, it's kind of like the real world. So you have a couple of things to do in life, right? It's either give or take, right? Or you can share, okay? So I'm going to go through my logic, and it may not make a lot of sense completely, but I want you to sit there and give it a little bit of a thought, okay? So, not saying that you guys are thieves or any of you guys are criminals or anything like that, but if you were, right, would you steal from somebody that lives right next door to you?
Oh, far away.
No, right? You would steal from somebody who's in another town, right?
Yes, because they don't know
Okay.
me.
And that's just kind of common sense, right? Just a little bit of common sense there. Yeah, no, maybe. Okay, so now chemicals, or most chemicals, I should say, or most elements or atoms, they kind of want to be like the noble gases, and that's where we're going to kind of start, and then we'll talk about that whole stilling and everything and where it comes into place. You guys know the noble gases? Have we talked about the noble gases before?
Yes.
These guys are the noble gases. Why are they noble? Why do you think they're noble?
Because everybody wants to be like the noble gases.
Well, because everybody wants to be like them. They're noble because they have stability, right? And so, like, as an adult, as a kid, we didn't care so much about stability. We cared about being cool, right? So we thought about the noble gases as being cool. Now, as an adult, we want to think about them as being stable because, I don't know about you guys, isn't part of the reason why you guys are taking this class is that you want to reach a point of stability so you can support yourself, bring in that dough, buy those cars, have those women or men, you know, right? Nobody agrees with me?
I agree.
Yes.
Okay, so I'm sitting there saying y'all are full of crap because, you know, I know it's early. You guys need to wake up, but the reason why we do it is because we want stability, right? And so the elements on a periodic table are the same way. They want to be stable. And the way that you become stable is by getting your octet filled. And what do I mean by that? I'm going to go into a lot more detail a little bit later, but right now, to get your octet filled is going to be like the noble gases. That basically means that you have the right number of electrons in that outer shell and you're happy, right? You're rich and happy, or fat and happy, right? Okay, so you're in a good state. And that's where the noble gases are at. All of the other elements on the periodic table, they're not, and they want to get there. Okay, so for instance, the halogens. These are the halogens. This group here, how far are they away from being a noble gas?
One
One
electron.
electron.
One electron, right? So they need one electron, and they'll be exactly like a noble gas, and that's going to make them happy. Now, if you're just this close away from being a millionaire, right? Wouldn't you do just about anything to get there?
Yes.
Of course.
Okay, they're going to be the same way. So they're going to be really reactive, right? So halogens, they're pretty reactive. They want to react because they're this close to get there, okay? So if they get that one extra electron, they're able to get there. So they're going to be willing to sit there and take. In most cases, they're going to want to take, and then, or share to sit there and get it. So they'll share an electron with their neighbors. So these guys, these are all these guys here are all non-metal, right? And they're on the same side of the periodic table. They're going to share with those guys, right? They're going to be cool to share with those guys. You're like, yeah, let me borrow your bike. You know, I may keep it for a week, but you'll get it back, right? So they're going to want to share in that case. And they're going to share in most cases unevenly, the halogens especially. Halogens are going to want to share unevenly because they're one away, so they're going to have a stronger pull. They're going to want it more than the other guy does. Okay? Now, oxygen and the chalogens, so these guys, they're two away, right? Their pull isn't going to be as strong as the halogens, but it's going to be pretty strong because they're only two away. Nitrogen, well, it's further away, right? So then its pull isn't going to be as strong as oxygen. And then we have carbon. Carbon here is in the middle, right? So how many away are we away from being a noble gas if we're carbon?
4 electrons.
4 electrons. And then how many away are we, how many electrons would we have to get rid of to be like helium?
3. Because you need one
1,
electron, right?
2, 3, 4. So they're in a kind of, they're like in that perfect spot, right? So they're 4 away, right? So they're 1, 2, 3, 4, or 1, 2, 3, 4. Now these guys, like nitrogen, it needed just 1, 2, 3, right? Or if it tried to get rid of it, it would be 1, 2, 3, 4, 5. So I'm going to ask you a personal question. So if you could earn $500 by mowing 3 lawns or $500 by mowing 5 lawns, what would you do?
The 3.
3.
Why?
Easier.
Less.
More money.
More money for less work.
More money for less work, okay? So that's exactly what these atoms are going to be like. They want more money for less work. They're lazy, just like us. They're not going to try to do any extra work that they don't have to do. So it's a lot easier for nitrogen to gain 1, 2, 3 than to lose 5. That's a lot more work, okay? So it's going to try to find the easiest way to keep its energy as low as possible, you know? More bang for your buck, right? Kind of like that mentality. Okay, so carbon, we said, is how far away from being a noble gas? How many more electrons would it have to gain to be like neon?
4.
4.
4. Okay, and then how many electrons would it have to lose to be like helium?
4.
Okay, so it's kind of like that in the middle. So did I tell you about carbon being a whore?
No.
No? Okay, so carbon's a whore, right? Part of the reason why carbon's a whore is because it's right there in the middle. It can do 4 bonds, right? So it likes those foursomes, right? Kind of kinky. And it's kind of like, well, what do you want, maybe, right? But depending on who it's paired up with, it's going to be willing to, oh yeah, you can share. We can share. Oh, you can have it most of the time. I don't care. You know, so it's kind of like flexible, right? So it could either give, it could take, it could share, right? And it doesn't really, you know, it's like, you know, whatever you want to do. I'm here to satisfy you, right? Okay. So carbon, it's very flexible. 4 bonds, foursomes, right? Share, give or take, doesn't matter, right? So it can go either way and it can be satisfied, okay? So that's why I think of carbon as being a whore. So it's kind of like in that middle point, and that's going to make carbon the center of a lot of things, right? What is the center of life?
Carbon.
Carbon. Why do you think carbon's the center of life? Because carbon's a little bit of a whore, right? Can do those foursome, 4 bonds, right? Attach the 4 things, kind of kinky, you know?
Are you going to show your party video, Dr. Henry?
I am. I'm getting there. I'm just building up for the suspense, right? So, so you guys kind of get an idea, okay? So these guys here, these metals, they have options. Either they have the option of gaining electrons. So if you're lithium, how many electrons would you have to gain to be like a noble gas?
6.
So you'd have to gain 1, 2, 3, 4, 5, 6, 7.
Oh, 7.
Or you could just lose 1. what do you think you're going to do?
Lose it.
You're going to be like, oh, dropped it. Oops, I don't know what happened, right? So you're going to want to lose it. So these guys, this guy is, again, one away from being a noble gas. If it loses one electron, it'll be a noble gas. Do you think that's going to be pretty reactive? Yeah, no, maybe?
Yeah.
Yeah, right? Because if you're so close, you're going to be like, yeah, I'm anxious to do it, right? So
Yes.
in that case, lithium is really quick. If you put in water, it starts smoking and getting all excited and flaring up because it's pretty reactive. Sodium, exactly the same way. Potassium, exactly the same way, right? If we expose it to air, same thing happens, right? So we got to keep that metal kind of under wrap. We have to put it in oil to keep it from reacting. Oil is basically carbon, a lot of hydrocarbons, right? And since it's all hydrocarbons and carbons, like, yeah, so it's not going to really want to react so much with it. It kind of keeps it inert under those circumstances. But as soon as you get all of that oil off, it starts wanting to react with the air. It wants to react with the, or I should say, the oxygen in the air. It wants to react with water. It's going to be very reactive. Okay, now these metals here, so these guys are called alkali metals. And again, that alkali, it has a punch to it, alkali, right? Kind of a punch in that, the name, wouldn't you guys say?
Yeah.
Yes.
Okay, now these metals are called alkaline. That kind of tones it down. Oh, they're alkaline metals, kind of in the name, right? Alkaline. So these guys, these metals are less reactive because they're two away, right? So they have to lose 2 electrons to be like a noble gas. So they're not going to be as reactive as the alkali metals. They're alkaline metals. They're going to be a little more chill, you know, but still want to get there, right? But they're a little subtle about it. And then we'll talk about the transitional metals. These metals are just a hot mess, right? So sometimes they want to lose 2 electrons. Sometimes they want to lose 1 electron. Sometimes they want to lose 4 electrons. So depending on which one it is and who they're working with, they can vary. They're a hot mess. So these metals, they're transitional, you know, changing, going through changes, right? And that kind of defines them pretty well because they're kind of a hot mess. They're going through changes. Okay? So you guys kind of get the gist of everything? Okay? Yeah, no. So you guys kind of understand it now, right? So now the key is here is that it's going to be electrons. A lot of chemistry is centered around electrons. Okay? Whether you're going to be sharing electrons, whether you're going to be losing electrons, whether you're going to be gaining electrons. Okay? Now if you're losing or gaining, right? That means that you're going to have a charge associated with you afterwards, right? So you're negative and you're positive. So what happens if you bring a negative and positive together?
They attract.
They attract, okay? So an ionic bond is just the attraction using those attractive forces of a negative and positive. So ions are going to be forming ionic bonds. Does that make sense? Are you with me?
Yes.
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 Okay, so ions are going to be forming ionic bonds. Makes perfect sense. Now, covalent bonds, or bonds where you're sharing, right? In that case, covalent bonds are going to be the guys that are on the same neighborhood. So non-metals form covalent bonds with each other because they're going to be sharing electrons. So their desire for it is going to be kind of the same. You don't have one that's wanting to give and then that one that wants to take, right? So like in the case of, let's go back to the periodic table, these guys, all your metals, those guys are going to be your givers. They're going to be giving up electrons to try to be like the noble gas. These guys, your non-metals, those are going to be your takers. They're going to want to take those electrons. Now, this holds true for most things in most cases. There are going to be some exceptions that we'll talk about later on, but for right now, that's going to hold true. Okay, you guys got that? So, who's going to be forming covalent bonds? Metals or nonmetals?
Non-metals.
Nonmetals. So your nonmetals are going to be forming covalent bonds where they share electrons. Where your metals, if you have a metal and a nonmetal together, it's going to be about give and take. Your metal is going to give up an electron. And if you lose an electron, what is that called? What are you called then?
Anion.
If you lose an electron,
Oh,
what's going to
cation.
be your charge? It's going to be a cation, right? Why is it a cation?
Because it's positive charge.
Because it's positive, right? Okay. Remember the bad joke that nobody laughed at the last time? Okay. So metals are going to lose an electron and they're going to form a cation. Non-metals, they're going to gain an electron and they're going to form an anion. Okay. And then when you get a cation and an anion together, you form a ionic bond. Okay. Now this bond, this ionic bond that's formed, it has to be a total neutral charge. That means it has to totally balance each other out. Okay, to be a ionic compound or to form a complete ionic bond. Okay, so are you with me so far?
Yep.
Yes.
So let's talk about potassium here, right? Since we have potassium already up in our highlights. So potassium is going to form, what is going to be the charge? What type of ion is potassium going to form? Where's potassium located?
Right?
What was that?
It's just negative.
Is it going to be negative?
Positive.
It's going to be positive cation.
It's going to be a cation, so it's going to be positive. So it's going to be K plus, right? Because why? Is it gaining an electron or is it going to be losing an electron?
Losing.
Losing.
It's going to be losing an electron. Okay, let's say it bonds with bromine. So bromine, is that guy going to be positive or negative when it forms an ion?
Negative.
Negative.
Negative because
It's gaining an
It's
electron.
gaining and then
it's gaining. So it's going to gain that electron that potassium it gave up. Okay, so since one gave it up, the other one is going to take it. Okay, so bromine takes that electron and said, hey, dude, I just need one, right? You could either give it to me or I'm going to take it from you, right? And then potassium says, okay, I'll give it to you, right? And then afterwards, they hook up. Because potassium is positively charged and bromine is negatively charged. And so when they come together, they kind of balance each other out, right? So kind of like when you guys were in high school, you always wanted to hook up with the bad boy or date the bad boy or the bad girl, depending on who your preferences, you know, so. Although some of you guys may be the bad boy, the bad girl. Right, Maddie?
What?
Just teasing.
I'm
Okay.
a good soul.
Okay, so you see how that works, right? And they have to balance each other out perfectly, right? So if one has a positive charge, right? So then you need to sit there and have enough to balance out the other one. So if one has one positive charge, the other one either has to have one positive charge or you're going to need multiple to account for it. Okay, so let's say we have something like this. Instead of bromine, let's say we have potassium and oxygen. So what is going to be the charge on oxygen? How many electrons is oxygen going to want to have? Oxygen.
Oxygen and -2.
two.
Okay, so oxygen is going to need to gain 2 electrons. So how many potassiums am I going to need to balance out oxygen?
2.
2. So I'm going to need 2 of these guys. The fact that I have a coefficient in front of it means that I have 2 potassium ions. But when I write it as a chemical compound or an ionic compound, it is going to be K2O. Do you guys see that?
Yeah.
Okay, so what happens if I have, instead of oxygen, if I have nitrogen? What's going to be the charge on nitrogen?
-3.
-3. How many potassiums am I going to need to balance it out?
3.
Okay, so what would be my chemical formula for potassium nitride?
K3N.
K3N. Do you guys get that? Can you
Yeah.
see it?
Yeah.
Okay.
Yeah.
Okay, pretty simple, right? Not too hard. It's just simple math. Okay, so let's talk a little bit more, right? So when we talk about the potassium ion, we call it, and let's say we just have the ion itself, we call it potassium. Potassium ion. Okay, and we know potassium is in that first column. It's always going to have a +1 charge, right? We've kind of already talked about that already, right? So that potassium ion, we know is going to be a +1. So we know what to write down when we hear potassium ion. Now, this guy here, we call this guy, instead of the nitrogen ion, we call it nitride. We put IDE at the end. Okay, so that tells me it's at the end for one thing, and it also tells me that it's a negatively charged, okay, ion. So we would call it the nitride ion, because then it tells me it's a negatively charged ion, and we put it at the end. So the way that we would name this, we would call this guy potassium nitride. Okay. Are you good? Simple?
Yes.
Okay. So I'm going to test you back. Let's go back to that oxygen molecule. So we said oxygen is going to have a what charge?
-2.
-2.
Okay. So the chemical formula again would be what? How many potassiums am I going to need to balance it out?
2.
2.
2.
Okay, so then my chemical formula would be
K2O.
2O.
K subscript 2 O. Okay, so then what am I going to name it?
Potassium oxide.
Okay, so I'm surprised nobody's asked me this question. So did you guys notice that there's no di potassium oxide? Did you guys notice that?
Mm-mm.
You didn't notice that?
I
Good.
noticed it now.
Oh, you notice it now, right? So, because we know that there's 2 potassium, right? But we know there's 2 potassiums because it has to balance out the charge on oxygen. So the thing is, we always know that group 1 metals will have a +1 charge. We always know that group 2 metals will have a +2 charge. But remember I told you about our transitional metals? That they're a hot mess? And so they don't have something that's always consistent, right? So we need a way of dealing with these hot mess metals, right? And I'll talk to you about that here in just 1 second. I want to give you another example before we move over to that. Okay, so let's assume that now we have magnesium. Okay, so if I have magnesium, what is going to be the charge on magnesium?
+2.
It's going to be +2. So what are we going to name this ion?
Magnesium ion.
Okay. So if I have, let's do, so if I have iodine, what's going to be the charge on the iodine?
-1.
1.
Oops. Okay, so what am I going to name that guy? That ion.
Iodide.
Iodide. Okay. And we put ion, sorry. Okay, so when they come together, how many iodide ions will I need to balance out the magnesium ion?
2.
Okay, so the chemical formula is going to be
MgI2.
and we're going to call this guy
Would it be magnesium iodide?
that's right. It'll be magnesium iodide. Good job. Piece of cake?
Yep.
Yeah.
Okay, simple, right? It's not too hard.
Oh, wait, there's more.
Of course. Okay, so now we need to talk about those transitional metals, right? So the transitional metals, they have options, right? Remember I told you they can go through changes and stuff like that. So I'm going to go ahead and erase this right now. Oh, let's do one more challenging one before we move on. Let's instead of doing iodide, let's do phosphorus. So the phosphorus ion, or we call it phosphide, is going to have what type of charge?
-3.
Okay, so the phosphide ion is going to have a -3 charge. So then how many magnesiums am I going to need to balance out the phosphide?
3.
And how many phosphides or how many phosphides am I going to need to balance out the magnesium? Or both situations.
3 and 2.
Okay, so I'm going to need, you said 3?
3 magnesium, 2 phosphides.
Okay, so altogether that'll give me a +6 charge, and then this will give me a -6 charge. So that works out. So what do we call this guy?
Magnesium phosphide.
Okay. Piece of cake?
Yep.
Okay. So let's talk about those transitional metals. Now, since those transitional metals could have different charges associated with them, right? Since they're kind of crazy, you know, going through those changes. So let's say we have iron, and it has a +1 charge. So in this case, iron has a possibility of having +1, +2, +3, +4. So depending on who it's working with, how you use it, under which circumstance you use it, it could have different charges associated with it. So since that's the case, we need a way of determining, is it going to be that +1, +2, +3, +4, right? The way that we do that is we call this guy, and it has to be given to you or told to you, or depending on who you're pairing up with, right? We call this guy iron. We use Roman numeral I, ion. Okay, so we use Roman numerals. You guys know your Roman numerals? I means what?
1.
I means what?
Just 1.
I, 2 I's.
2.
Oh, 2 I's too.
2.
Okay. B means what?
5.
5. IV means what?
4.
VI means what?
6.
X means what?
10.
10.
Okay, you guys got it. Okay. So in this case, I have iron 1. So how many irons will I need to balance out this phosphide?
3.
3. Okay, so what would be my chemical formula?
They balance out, so it'd just be FEP, right?
Did I need 3 of these? Because this has a plus charge. So it would be
Fe3P.
Fe3P. Okay, so then I would name it. What do you guys think I'm going to name it?
Iron phosphide. Iron 1 phosphide.
Iron 1
3.
phosphide. Okay? Piece of cake?
So you determine the charge of the transitional metal based on your negative ion?
Yes, if you're given the chemical formula. But if you're not given the chemical formula, you have to pay attention to the Roman numeral. So here we have the Roman numeral, right? So the charge of that ion is +1. Okay, so let's say I had, gonna erase some things here. Let's say I had iron 2. What is going to be the charge of that iron?
2 positive.
Okay, it's going to be 2 positive. Okay, so then how many of these iron will I need to balance out my phosphide ion? How many iron 2 ions will I need to balance out my phosphate ion?
3 and 2, right?
3 and 2, yeah, 3 to 2 ratio.
3 and 2. Okay, so then my chemical formula is going to be
Fe3, P2.
okay, piece of cake, and then the name.
Iron 2 phosphide.
Wait, Dr. Henry.
Yes.
So the Roman numeral has to be provided to us first, and then that's how we know what the charge is?
Yes, that's right. Or if you're given the chemical formula, based upon the chemical formula, you can determine what that charge is, right? So let's say, for instance, I gave you this. Let me give you an example. Because right now it's kind of a big blur. Okay, so let's say I gave you Fe. So if I gave you Fe3P4. Okay, so we have the chemical formula. So what would I call this guy? Any guesses?
It'd be iron 4 phosphate.
That's right.
Okay, so
Iron phosphide. Oh, okay.
Iron 4.
keep up with this.
Phosphide. Okay. The way that we knew it was iron 4 was how many phosphides do we have? And
4.
so we had 4 phosphides, right? We know that each phosphide has a what charge associated with it?
-3.
A -3. Okay. So then how many irons did we have?
3.
So we had 3 irons. So what must be the charge of each of those irons for this to balance out? So we have 4 times 3, but 4 times -3 is what?
12.
Okay, so it's -12. So if we have 3 of these, what must be the charge of these, of each of the iron, for it to balance out that -12?
-4.
You mean +4?
If you're getting it equal to -12, you need a -4.
I said to balance it out, not getting it equal to.
Oh,
right?
then yes, 4.
Okay, so then it has to be plus. And we know it's a metal. We know that all metals are going to have a plus charge. If it's the metal by itself, it's going to have a metal ion by itself, it's going to have a plus charge. You should always remember that. So you don't, so it'll be, 4 plus. Be consistent. Okay. So then we know, now we have the charge with it, right? And that charge is going to be the same as that Roman numeral. Okay, so the Roman numeral tells us the charge. Or we can determine the charge by who it's paired up with. Do you guys see that?
Yes.
Yes.
Okay. So we've talked about transitional metals, right? So we know how to work with those transitional metals. They're not too hard. It's not too complicated piece of cake.
Tell us why.
Yeah, they're easy.
Oops, Junior froze. Oh, there you go. Turn your mic on, Junior.
Okay. So let's see. So we talked about transitional metals. We talked about just the our standard alkali and alkaline metals. So then we've talked about ionic bonds. So that pretty much covers our ionic bonds right there. Transitional metals and our regular metals, right? Feeling good?
Yep.
Okay,
Yes.
so let's see if we can make it a little more complicated, right? So let's say I want to know about the phosphate ion, or no, let's do the nitrate ion. So let's do nitrate. So if I have iron 2, what is the chemical formula for nitrate?
NO3 negative.
So then how many nitrates am I going to need
2.
to balance out my iron 2? Okay. Oops. Okay, so then my chemical formula is going to be
Fe.
And then nitrate 2.
so like this.
Don't you put it in parentheses?
That's right. So we'll need the parentheses to let me know that I'll have 2 of those nitrates. Okay. And then what would I name it?
Iron 2 nitrate.
It would be called iron 2 nitrate. Piece of cake?
Yes.
Okay. Let's do copper 2 per phosphate. Okay. What would be the chemical formula for that?
Copper with a positive 2 charge.
Okay.
And then perphosphate is PO5 3 negative.
Okay, so how many of those am I going to need to balance out
So
my
you
coppers?
You need 3 copper and 2 perphosphates.
Okay, so then my chemical formula is going to be
Use words, woman.
Cu
3.
No, you weren't surprised? You figured it out from the clue?
and then
Parentheses.
parentheses PO5 3 negative.
Let's play again.
Do I put the 3 negative?
You want to do the 3 negative, you'd finish it and put a 2.
Oh, yeah, because the 3 goes to the.
Yeah, you don't include the charge.
That's right. So you don't include the charge, right? Remember, charges, they're negated when they're together. So you don't include them when they're together. Okay, so that would be your answer. Cu3, PO5 2. Questions, concerns?
No.
Pretty simple, right?
Mm-hmm.
Just adding and subtracting, and a little bit of multiplication. Okay. So clear. So that brings us to okay, so we've already talked about the charges and the association with them. So you're feeling very comfortable with that. So some of the properties that are associated with ionic compounds. So they're typically a solid. So they're typically solids. They are non-conductive in their solid form. So when you have the ionic compound together, they won't conduct electricity, right? So if you stick electrodes in just dry salt where there's no water or anything like that, you're not going to be able to conduct electricity, okay? But if you melt it or you put it in an aqueous solution, then you're able to conduct electricity because you allow those ions to kind of be free, right? So this is an example of that. Okay, so here we have just dry sodium, right? So you get no electrical current. So if we melt that, I'm saying sodium chloride, we have dry sodium chloride, just salt, dry salt. So you get no electrical current. So as soon as we melt that salt, we actually will get electrical current. Okay, so we've talked about how to do the molecular formulas, right? So often in nature, we have various gems and things that we kind of think are pretty fancy. So here, this is aluminum. Aluminum has a +3 charge. Oxygen has a -2 charge. So when we put it together, we have Al2O3. Okay. And so the 2 aluminum will have a total of a +6 charge. The 3 oxygens will have a total of a -6 charge, and they balance each other out. Okay, so this guy is a blue sapphire. The blue sapphire is aluminum oxide with a little bit of iron and titanium to kind of give it its blue color. Okay, so aluminum oxide is a precious jewel that we kind of think is pretty fancy, right? So we've talked about polyatomic ions and how they relate, and the fact that we have to use the parentheses when we have multiples of them. Okay, and so if there's more than one here, we're going to have to use parentheses, and then we use the subscript to tell us how many of those polyatomic ions that we have. Okay, so we're going to stop right here. We're stopping at slide 84. I know we only went over like what, 2 slides.